Hey guys, so today I wanted to talk about the Dirac function, which is something I talked about last time in the neural encoding lecture, and I realized it's not easy to understand, so that's why I wanted to make a separate video on it. So before I talk about the Dirac function, I wanted to talk about something called the Heaviside step function. It was actually named after a guy, an electrical engineer. I think his name was Oliver Heaviside, and he did a tremendous amount of work in differential equations. So this concept of the step function and the Dirac function goes far beyond just computational neuroscience. So the way it's defined, it's called theta or h sometimes. Sometimes it's just denoted by a bold 1. But let's say I use theta. So the way it's defined is theta of t is 0 if t is less than 0, and 1 if t is greater than or equal to 0, right? So you might have seen something like this before. It'll look like a jump discontinuity. So it'll be something like this, right? And you'll see why I'm drawing this line right here. Usually you will not see this, but the reason I'm doing this will make sense when I talk about the Dirac function. So up to here it's 0, and then it just jumps up to 1, right? Now, when we come to the Dirac function, the way it's defined is as the derivative of the Heaviside step function. So what does this mean? Well, we know what the Heaviside step function looks like, right? So the derivative, well, here it's easy because the derivative is just the slope of the tangent line, right? Here the slope of the tangent line is 0. So Dirac is going to be 0 everywhere along here, right? Here it's going to be also 0 because the slope of the tangent line is 0, right? So here it's going to be 0. So there it's pretty easy. But at this point is where it gets a little weird. Some people say that the Dirac function at 0 is undefined, but I'll call it infinity because the slope of the tangent line looks like it's infinity, right? And you might think positive infinity or negative infinity, or what does that mean? And I'll say right for now, don't worry about it. We're just going to denote it by an arrow that spikes upwards. Okay? This is the way it's actually denoted. This doesn't have a value. Like, this is not like 8 or 1 or whatever. It's just an infinitely large arrow. Okay, so let's say we wanted this arrow, this spike, somewhere other than 0. Well, as you know from functions in general, we can just do a phase shift, right? We can just do delta of x minus c. So if we wanted it at, let's say this place is b or something, then we wanted an arrow here. Well, we could just denote that by delta of x minus b. And this is the important thing. The delta function, the Dirac function, always spikes at 0. So delta of just b will be 0. Okay, I'm shifting the entire function over. So before it was here, I shifted it over to here, right? It's not like this is a new function. Okay, so now we come to the neuron thing I was talking about before, right? So this is how I defined the neural response function, which denoted the spikes that the neuron took over time, right? I took it as the summation of a bunch of delta functions. So what does this actually mean? Well, let's just plot it one by one. You know that delta of t minus t1 is a spike at t1, right? Because we just phase shifted the delta by t1 to the right. Okay, so we get a spike at t1. Same thing for t2, and so on, right? And for each one of these spikes. And let's say t3 is closer, right? So that's how I denoted it. It's just a bunch of spikes at different time intervals. Okay, so now you might be wondering, wait, so what is delta of t of 1, right? How does that correspond to the action potentials we were talking about? Because action potentials aren't infinite or negative infinite, right? So this is where the actual definition of the delta function comes in. So as we said, delta of 0 is murky. We don't actually know what it means. However, the way we define it is if we take an integral around if we take this integral, right, of f of x, where f is any function, times delta of x minus a times dx around point A, right? Then we'll get f of a. So let's say this is, for sake of example, this is point A. Okay? And let's say, then what is delta of x minus a? Well, it'll just be an infinitely long spike over here, right? So when we actually integrate this, what are we doing? Well, here, anywhere here, then delta will just be 0, right? So we don't have to worry about any of those integration parts, right? Because if we have like -6 or something, then delta of the delta function will just get 0, and the integral will be 0, right? Everything inside is 0. But around here, well, let's take it piece by piece. So we have the delta function, which is an infinitely long spike. We have dx. So dx is an infinitesimally small change in x. And we have f of x, which is this part right here. Now, the way you can think about it is that dx and this infinite delta kind of cancel out. You know, mathematicians would cringe upon me saying this, but you can kind of think of it that way, conceptually. So if they cancel out, then what do you get? Well, then you just get f of a. And this is the definition of the delta function. If you wanted to do that more mathematically, you could do a minus something, the integral from a minus something to a plus something, because, you know, you really don't care about the stuff before, right? A small, like, epsilon, you could say. You could also do the integral from negative infinity to infinity of the same thing, but obviously the stuff before would cancel because the delta function would just give 0. And this is the way the delta function is defined. Or another way, which I'm going to talk about right now. So I said the Dirac function. I keep exchanging delta and Dirac. The full name is the delta Dirac function. People call it one or the other. It doesn't matter. But it's actually not a function at all. Technically, it's a distribution. So the way it's defined is if we had a normal distribution, like any generic normal distribution, and we kept reducing the standard deviation up to where the standard deviation was 0, then that would get the Dirac function. So if you wanted to get mathematical about it, then you'd say that the limit as the standard deviation approached 0 of the normal distribution, this is the formula for the normal distribution, in case you haven't seen it before, then it approaches a delta distribution. So, but for our purposes, you can think of it as a function that it outputs a spike at some value, and that these spikes are used to represent action potentials. So I hope that helped and gave hopefully some clarification on the delta function. But the delta function goes far beyond just computational neuroscience, as I said before. I can't, like, just off the top of my head, it's used in probability when it comes to mixed distributions, impulses in physics, when you want to represent infinite flux, in accounting, if you want to represent someone putting money into their account at an instant. Like, let's say I put in $10 at an instant and I want to see how that grows over time. So you'll undoubtedly encounter the delta function in your studies in the future. So hopefully that sheds some light on it, and that gave some context to the neural encoding video.